Good morning, everyone. Today we're going to see what is a gradient. Here we see what is the definition of gradient. Here, and differential calculus, we can introduce an operator d by dx. Usually, when we differentiate, we use d by dx. When applied to differentiable function f of x, it yields another function df by dx, because here we're going to differentiate a function with the name of f, so we can have df by dx here. In this section, we introduce another operator del. Here, del is known as a gradient to be read as del. It is given by an equation del equal to I dou by dou x plus j dou by dou y plus k dou by dou z. Here I, j, k are unit vectors. So in below we have the clear definition for a gradient. Here we have chosen a function pi with three vectors x, y and z. These values are real values, so we have a real valued function pi of x, y, z. So we can apply it into the gradient operator del. So we can have del pi equal to I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z. Here we can construct these term into initial term, so which is constructed like summation I dou pi by dou x. So we summed the whole term with a single term. So this is what the definition of gradient. So nextly we can have uh, del pi is called gradient of pi and it is denoted by grade pi. So we can also denote del with the name gradient. So gradient pi we have. Thus the gradient of a scalar function pi is a vector valued function. So here they have defined the gradient of a scalar function. If we have chosen a function in scalar form, then we calculate the gradient, then the function will be a vector valued function. So here we can see the example. Here the pi function is given like x y square plus y z cube. So initially we do gradient pi. So here we have to apply the symbol of gradient. So we have del pi, which is equal to we have the formula I dou pi by dou x, j dou pi by dou y and k dou pi by dou z. So instead of pi we have to substitute the pi value x y square plus y z cube. So now we going to differentiate x, y and z with respect to I, j and k. So here we have the gradient value. So that's it. Now we're going to see the geometrical interpretation of a gradient function. So for that we have chosen a pi function, pi of x, y, z. This function is a scalar valued function. So now we're going to choose a point P. Here we have a x-axis, y-axis, z-axis with respect to the point x0, y0, z0. So this is any point in that field. So let the pi function be applied by the values of x0, y0 and z0. So let we have chosen pi of x0, y0, z0 equal to c, which is a constant value. Then the equation pi of x, y, z equal to c represent a surface. So here we substitute the point into the surface. So the pi function refers a surface. Obviously x0, y0 and z0 lies in the surface because the point lies on the surface. Okay. Along the surface d pi equal to 0. When we differentiate the pi function, we can have d pi equal to 0 because the function is a constant function. We have chosen earlier pi of x0, y0, z0 equal to c. So when we differentiate a constant function, we can get 0. So that is dou pi by dou x dx, dou pi by dou y dy, dou pi by dou z dz equal to 0. Here we can substitute the gradient value del pi and we can have dou pi by dou x instead of dr. So dr, here dr is a directional derivative. Here dr is defined by I dx, j dy and k dz. Here del pi is perpendicular to dr as long as represent a change from P to Q, where Q remains on the surface pi of xy is equal to C. Here we have del pi is normal to the tangent surface. So del pi value, the gradient of pi, that value normal to the tangent surface. So we have chosen a tangent surface with the point P of x naught, y naught, z naught. Here we can have the unit normal to the surface pi. We have already chosen pi of x, y, z equal to C, which is a constant function. Here we have derived the n value, n equal to del pi by modulus of del pi. So this is what the tangent representation of the pi function. Before that, we have to clear about directional derivative. So here we have chosen a unit vector A and the component del pi. So the directional derivative is defined by the direction of A. It can be interpreted as a rate of change of pi at some point in a direction A. That is what direction vector with respect to a unit vector. So A is a unit vector here. So here we have a note, we have chosen a point P, x, y, z and Q, x plus del x, y plus del y, z plus del x. Be the two neighboring points. We have chosen 2 points P and Q. With the 2 points we going to find out the distance. So we have to derivate that d pi by ds. We have to find the distance. So we have to derivate with respect to s. So we have ds here. D pi by ds equal to dou pi by dou x dx by ds plus dou pi by dou y dy by ds, dou pi by dou z dz by dz. So each and every vector we have to differentiate separately for x, y and z here. So finally we have dr by ds dot del pi. So we constructed the values of x, y and z into del pi and the directional derivative by dr by ds. That's it. So nextly we have since dr by ds is a unit vector and dr by ds dot del pi is a directional derivative. Here we mentioned that dr by ds is unit vector and the directional derivative is with respect to the pi function. So here pi in the direction of dr by ds, pi travelled in the direction dr by ds. Here the value d pi by ds has a maximum value with respect to del pi and dr by ds. That was a directional derivative. So it has a maximum value with respect to the directional derivative and the pi function. The maximum value of the directional derivative take place in the direction of del pi and its magnitude is modulus of del pi. So we define the magnitude by modulus function. So we have a modulus del pi here. In below we have see the equation of the tangent plane. So for calculating the tangent equation we have to choose a pi function pi of x by z which is a constant function with the point a x naught y naught z naught. So we have chosen a point x naught y naught z naught. Let p of x y z be any point on the tangent plane whose possession vector. So here we have to mention a possession vector because we are finding the tangent equation. So possession vector is r. We already know that what is r. So r equal to xi plus yj plus zk. At this point contact so this point contact with the tangent plane, so it converted into that x, y, z converted into x naught, y naught and z naught. So then we have to subtract the value from r to r naught. That is what the intersection of the tangent plane to the normal surface. So here finally we have at the point x naught, y naught, z naught, we have the equation r minus r naught del pi equal to 0. That is what the equation of the tangent plane. In below we have the equation of the normal line. That equation is what is the difference between the equation of tangent plane equation and normal line equation is nothing but a tangent plane equation we have dot product. So normal line equation we have a cross product. That is what only difference between the two. So nextly we have finally we got the equations for tangent line and normal plane here. So nextly, so we conclude that r minus r naught is parallel to del pi dot del psi. So here we have chosen 2 points del pi, two gradient function, pi function and psi function, to find out the curve along the two surfaces intersect. Okay, so here we have chosen a pi function and psi function to find out the intersection of two surface. So we have chosen r naught equal to x naught I, y naught j and z naught k, and r equal to xi, yj and zk be the two position vectors. So from that we can find out the equation of the tangent line at a point and the equation of the normal plane at a point. So finally we have conclude what are the equation of tangent line and normal plane. So hence that's it. Thank you.